Let's talk about the periodic table. So here's how you can use this video. Throughout this video, there'll be slides with text highlighted in green. If you're using this to take a notebook or to use a notebook, write that. Those are the key ideas from this video. Also, there's going to be some questions that are written in blue. Those are the blue text. Those are questions for you to answer or for you to consider. Also, throughout this video, there's going to be one visual code, which will show up on the screen, and one verbal code sent by myself at some point throughout the video. There's just 3 random numbers each, so pay attention. All right, let's get started. So how is the periodic table organized? So the periodic table is a chart that shows all of the known elements in the universe. So it's arranged by atomic number. That's the number of protons in each atom. So you can see this periodic table that I have. It's got a little sample there. That's chlorine. Chlorine is number 17. All chlorine atoms have 17 protons. If it doesn't have those 17 protons, it is not chlorine. And you can see it goes left, starting with 1 with hydrogen, top down all the way down to 118 oganesson. So that's the periodic table, yes. And the beauty of this is the one that we use. Mendeleev was the one that really created the one that we use nowadays. And the brilliance was when he created it to where he could predict elements that had not been discovered. He was very accurate in those properties. And that's the periodic table that you're probably most familiar with, that you see all the time, and the one that we're going to use. So all the elements on the periodic table is either a metal, a nonmetal, or a metalloid. So metals, shiny, solid, good conductors. Nonmetals, dull, brittle, poor conductors. And metalloids, they can have properties of each. You can see off to the right, this is the dividing line of it. And there's something known as the staircase on the periodic table. And you can see here that's where the metalloids are found. That really divides the nonmetals from the metals. You can see here hydrogen's a special case. It's a nonmetal. This really comes into play, though, when we start to talk about chemical bonding between metals and nonmetals, or nonmetals and nonmetals. This is just something to keep in mind for later when we get to bonding. So now let's get to how the periodic table is organized. Yes, it is by atomic number, but we've also got groups on the periodic table. Those are the columns. They go up and down. The elements in the same group have similar chemical properties, and the reason why is because they have the same number of valence electrons. And valence electrons, those are the ones in the outer shell. Those are the ones that determine the chemical properties of that element. And there are 18 groups in total. So if you look to this little graphic to the right, you can see here it's got group 1, 14, 17, and 18. They might have more orbitals, more shells, but each of them have the same number of valence electrons, so they're going to have the same chemical properties. Now, groups on the periodic table, they have specific names because they react very similarly, right? Group 1 and Group 2. Group 1 is the alkali metals. Group 2 are the alkaline earth metals. Now, Group 3 through 12, those are called the transition metals. Now, Group 13 is the boron group. And 14, 15, and 16, they're just named after same thing with the boron group, right? 13, 14, 15, 16 are just named after the top element in that group, right? So 14 is the carbon group, 15 is the nitrogen group, 16 is the oxygen group. And that's because these aren't as really as, I don't want to say famous, but just because these are the ones that really have a mix of metals, nonmetals, and metalloids. They're not really referred to as their name as much. Usually it's just the group number. Now the last two, these are pretty famous. These are really well used, right? Especially like group 17. These are the halogens because they have one. Their outer shell is almost completely filled except for one electron. So they really want that electron. They're very reactive nonmetals. And group 18, they have a completely filled shell. So that means they are really they're stable, they're unreactive. So probably the most famous one is like helium, like in helium balloons, neon signs. But these don't really react really with anything because they have a full valent shell. They don't really need electrons. They don't really bond with anything. So now let's get to the periods on the periodic table. So periods are the rows on the periodic table. They go left to right. There's 7 periods in total. As you move across the period, the elements change. That's where we go from metals to metalloids to nonmetals. Now, each period shows elements with the same number of electron shells. So if you look here, this one has period 1, 2, 3, right? That just tells you, well, how many shells do they have? So period 1 has 1 shell, period 2, 2 shells, period 3, 3 shells, and on and so forth. Now, periods don't really have like specific names. It just tells you what shells those electrons are filling. So, using these, you can really identify where the elements are on the periodic table. So it's just like a grid system here. So I'll help you out with some of these, and then I'll let you do the rest on your own if you want to pause that video. So I'll do the first couple for you, right? So group 1, period 2. So group 1, right? Remember, groups are those columns. Group 1, period 2, right? So periods, those are the ones, those are the rows, right? So that's going to be lithium. Right? I'll do the second one here. Group 17, okay, here's group 17 all the way over here, and period 3. 1, 2, 3, right? That is chlorine, right? So the first 5 are really going to be the ones in the main group, the ones in the first three periods. Now, after that, it can get a little bit tricky because now you're in like the transition metals. That can be really anywhere, right? So if I did this, the first one over here, right, I'll do this one here, right? Group 11, period 4, right? Here's group 11, period 4. So 1, 2, 3, 4, right? That is copper. So I'll let you pause this if you want to and do the rest. Just get some practice finding those elements on the periodic table using the group and the period. Now you can also go the other way, right? So you can you can look at for the element, say the group and the period. This one's a little bit trickier though, because this one you just have to find the element, right? The other one is just, hey, that one's easy. That's just a grid system. This one is just actually finding the element. So if I look at, I'll do the first couple over here, right? I'll do carbon, right? So carbon is right here. So now this is going to be group 14. I kind of covered it up over there. Period 2. Right? I'll do this next one over here. Sodium. Right there. So that is group 1, period 3. Now some of these, like the first 5 are the ones in the main groups up here. The next 5 are going to be really anywhere on the periodic table. So like iron, and it can get hard because like now you just have to find it, right? So iron is right here. All right, so you can see here that is group 8, period 4, right? So like I said, if you want to, you can pause, you can find the rest, just get some practice. So at this time, I'll go ahead and I'll give you that verbal code. The verbal code is 577. I say that again. The verbal code is 577. Now, there are a couple of special cases here. The inner transition metals. So we talked about the transition metals. The inner transition metals are the 2 rows below the main body of the periodic table. These rows include the lanthanides and the actinides. So I have the atomic numbers there. You've probably seen this on the periodic table. These are those 2 rows that are usually depicted below. And this is just to save space. It's not that they're separate from the periodic table. They are part of it, but it is just to save space. The inner transition metals are unique because of their electrons. They start to fill the f orbitals. I'm going to get to the orbitals in a second here, right? So lanthanides are often called the earth metals. Actinides, these are like the radioactive elements like uranium and plutonium. So I just want to show you like why they're depicted below the periodic table. It's really just to save space here, right? So if you look down below, this is what the periodic table would look like with the inner transition metals. Technically, they're a part of group 3. They're kind of just lumped in with group 3. But because it's just there's these 2 rows, like and they just have a placeholder. You just take them out, and then you can put them below just to save space. But yes, they are a part of the periodic table. That's what it looked like. It would just be very hard to print this in like a small page. So those are the inner transition metals. Now let's get to those electron orbitals. So there are regions around the nucleus where electrons are likely to be found. So in a Bohr model, they're just like, you just show the circles and those are the electrons that fill it. But there are these different like shapes of orbitals, and they have different energy levels. So there's different, we've got the s orbitals, the p orbitals, the d orbitals, and the f orbitals. And that's also how the periodic table is organized. That's why it has this shape. That's why some of them are lower below. That's why the transition metals are there, and it's because they're filling these different energy levels in the periodic table. And these are the different shapes to the orbitals. Remember, the electrons, they don't like just orbit around the nucleus. They do. It's like the electron cloud. It's just a probability of where they're going to be located. So here are the rules to filling electron orbitals. There's 3 of them, right? You've got Pauli exclusion principle. So if you look off to the right, the one closest to the text, no 2 electrons in an atom can have the same set of quantum numbers. When we're drawing this, you depict them with an arrow, right? One up, one down. That's what they mean by quantum numbers. Or spins, right? So spin up, spin down. But you can't, you have to have, you can have one up, one down in each spot, but you cannot have 2 of the same. There's Aufbau's principle. Electrons fill orbitals starting from the lowest energy level, and then you move up to higher energy levels. And that's that picture depicted right here, right? So you start with 1s, and then you go all the way up. Hund's rule. Electrons will occupy degenerate orbitals, orbitals of the same energy, singly before pairing up. So if you look here, what that means is that if I'm filling like the 2p orbital, it's up, 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 and then I start to go, down, down, down. I don't do this. I don't go up, down, down. So those are the rules when you're filling those orbitals, and it's very self-explanatory. So the electron configurations, that's just a shorthand. It just shows how the electrons are distributed in the orbitals in an atom, and it shows how they fill the s, p, d, or the f orbitals. And to find the number of valence electrons, this is how you can find it. Just look at the electrons in the outermost s and p orbitals, or s and d for those transition metals, and that's the number of valence electrons. So here's an example here, right? So carbon is atomic number 6. And you can see I have it off to the right how it's done. 1s2, 2s2, 2p2, right? So the first number, the large number, that is the orbital number, the period number. Then you've got the s, that's which orbital it is, and then you've got the exponent, that represents how many electrons are in that orbital. You can also write it as a shorthand starting with the last noble gas, because a noble gas has a full valence shell, and then after that it just kind of repeats. So you can say, hey, you know what, it's just helium plus 2s2, 2p2. So that really comes into play when we're talking about larger elements. So I'm just going to do one of these, and then I'll let you pause it if you want to do the rest, but I'm going to do nitrogen. So nitrogen, you can see here, is number 7, so I'm going to fill it, I'm going to fill it with 7. I'm going to fill it with 7 electrons here. So I start with the 1s, I go 1 up, 1 down. Okay, I go to the next energy level, 2s. So that's 1 up, 1 down. Okay. Now I go to the next one. Now remember, I have to fill up, up, up. So that's 1, 2, 3, 4, 5, 6, 7. So that's going to be the electron configuration for nitrogen. So I can write it as this. I write 1s2, 2s2, and then 2p3. Or I could write it that shorthand, starting with the last noble gas, which was helium. Oops, that doesn't look good. And then I can write 2s2, 2p3. So I'll let you go ahead and you can practice this. And once you get a hang of it, once you can look at this periodic table, especially one that has like the electron orbitals on it, it's really easy to fill out, especially starting with the last noble gas. Now, one thing I do want to note, if you look at these heavier ones, like especially uranium, some of those higher energy level ones, they're so close in energy levels that like sometimes the rules don't really apply too much up there. So if you look them up online, you're going to be like, well, wait a minute, this doesn't really follow the rules. It's just because some of those orbitals might overlap, especially at those larger numbers or those larger elements. But you can still practice using those rules with those larger numbers just to get some more practice. So, let's see here. Just remember, as a final thought, there's too much unknown in the universe to take a break from learning.